So we found a wonderful little theorem here. If the Wronskian is non-zero ever for any value of x, non-zero Wronskian, then we can conclude that the list of functions is independent. Now there's a temptation to say, okay, well yeah, but then what happens? What happens if the Wronskian is identically zero? What if this doesn't happen? Well, if this means independent, then wouldn't it seem like that if the Wronskian were entirely zero, wouldn't that suggest the functions are dependent? That's a very strong temptation, but it is false. There's a big warning here. Just because the Wronskian is zero, it does not mean that your functions are dependent. Now, if the Wronskian is zero, identically zero everywhere for all values of x, that does mean that this condition's not satisfied, and it means that you can't draw any conclusion. It means that you can't prove that the list is independent. That doesn't mean it's dependent. Okay. Now, importantly, the reasoning that we use to come up with this theorem, the reasoning that we used to get here, this reasoning here, it looks like it would turn around backwards, which would give us the result that we're interested in, that we're tempted to say. It would seem that you can turn that around backwards, but it doesn't really turn around backwards. Very importantly, this step here is not a reversible step. Let's take a moment to talk about what this says. This says that we have a non-trivial solution to this system of equations, but it says a little bit more than that. It says that we have a non-trivial solution of constants. These C's, you will recall, are constants, and they're constants because they are the coefficients in a linear combination that addresses dependence. So these C's here are constants. It is true that given these C's, which are constants, it does follow that the determinant has to equal to zero. Yes, indeed. But if the determinant is zero, it doesn't follow that these are constants. And in fact, that's exactly what goes wrong. In fact, when that determinant is equal to zero, there are some situations where different C's are required. And the book has a great example of this. I'll leave it to you guys to read that book example. The important thing that we have to remember here is that when the Wronskian is equal to zero, you do not get to draw the tempting conclusion that the list is dependent. Okay. Now, there's an additional statement that we can make. This is not in the book, but this is a really nice result, and it has to do with how you can fix this sort of in a certain category, restricted category of functions, and this is called the category of analytic, sometimes called real analytic. Here we'll just say analytic. Analytic functions. So I'll remind you, and you might recall these from single variable calculus, that a function is called analytic if its Taylor series converges to itself. So when you took single variable calculus, I'm sure that you talked about Taylor series. You can write down the Taylor series for a given function. You can ask the question of whether that Taylor series converges, and that's a matter of applying convergence tests. But there's some more work that has to be done to confirm that it actually converges to the thing that you were kind of hoping it would converge to, namely the original function that the Taylor series came from. And that's not immediately obvious. It requires doing some additional work that's done in Duke's single variable calculus courses. And you can show, in particular, that e to the x has this property, that not only does it have a Taylor series, let me do it like this, not only does e to the x have a Taylor series that you can write down, that Taylor series converges, but even more than that, its Taylor series converges to itself. The Taylor series for e to the x converges to e to the x. Okay, likewise, sine x has a Taylor series, which converges, and furthermore, it converges to itself, etc. So these functions are analytic. All right. So what? That's just a handful of functions. Well, here's some more good news. The sum of analytic functions is analytic. Products of analytic functions are analytic. Compositions of analytic functions are analytic. Fractions, now, mind you, not when you're dividing by 0, of course, but fractions with non-zero denominators of analytic functions are analytic. So not only do we have some analytic functions here, but anything that you can do to combine these together will result in an analytic function. Okay, so again, we repeat, who cares? What does this have to do with Wronskians? And let me remind you, our disappointment has come over the fact that we have had to accept that just because the Wronskian is 0, that does not allow you to conclude dependence. Very tempting. We just can't draw that conclusion. Wonderfully, if you know your functions are analytic, then you can. Wronskian being identically 0, then it follows that the list is dependent. Okay, so that's why this analyticity is important. Being analytic gives you a fix of this previous sort of problem theorem with the Wronskian. Now, in Math 216, you may use this theorem. That is fine. You do, however, have to be clear what you're using. So you have to be clear that you are writing down analytic functions. So you've got to indicate that the functions that you're looking at are indeed analytic. The reason I make a big deal out of this is that if you don't specifically note that your functions are analytic, then you're just claiming that when the Wronskian is 0, the list is dependent. In other words, you're just saying this. Right? If you don't note that the list of functions is analytic, you're just simply saying something that you're citing a false result. So in order to use this theorem, you have to say that they're analytic. Okay. Now, related to that, I don't want students to think that they should just assert everything in sight as analytic, just for good measure. When you cite this theorem, you should not cite whether the functions are or are not analytic, because they do not need to be analytic. And if you say, hey, the Wronskian is non-zero, and furthermore, by the way, these functions are analytic, it makes it look like you think that was necessary, which it isn't. So you lose points for that as well. So be very careful about this analyticity. When you're citing this theorem, do not cite analyticity. It's not necessary. When you're citing this theorem, be sure to cite analyticity, as it is necessary.